for joining. This is the Oracle Machine Learning Office Hours. I'm Sherry LaMonica, and today we have a special session with Miles Novotny, solution engineer specializing in analytics at Oracle. We will cover the in-database text analytics using the pre-built Explicit Semantic Analysis model, ESA, through Oracle Machine Learning for R. Imagine you have a large number of documents. These could be news articles, blogs, books, or any block of text. The point is that there are potentially millions of these documents, and you want to determine which documents are similar, identify topics, or perhaps categorize a set of words or documents. One way you can solve this problem is by reading through these millions of documents, and while you certainly learn a lot, you'll never finish. So you want to use an automated computational approach. This is where ESA modeling for natural language processing, or NLP, can be useful. In contrast to LDA, latent Dirichlet allocation, which is a very popular method for text analysis in NLP, ESA models don't find latent or hidden features, but instead use explicit features represented in the knowledge base, which in this case is a selected set of Wikipedia articles. Oracle Machine Learning provides a free pre-built machine learning model based on these Wikipedia articles, and the pre-built model was created using the ESA algorithm. Miles will be demonstrating using the Wikipedia model through the OML for R interface on Oracle Autonomous Database. But first, let's start with a poll. So what's your primary objective for today's session? And we'd love it if everybody would participate, because these polls help us direct us for our future office hours content and session. Oh, it looks like a really even split between all three. Interesting. If you have another objective, please put it in the Zoom chat or Q&A so that we can see that as well. Okay, thank you for participating. I'll turn the floor over to Miles now. Miles, take it away.
All right. Hello, everybody. My name is Miles Novotny. As Sherry said, I'm a solution engineer here out of Oracle's North America Specialist Hub. I'm going to be talking about how to perform in-database text analytics using a pre-built machine learning model. And our pre-built model today is a feature extraction ESA model based on Wikipedia articles. And I'll be showing that off through the soon-to-be-released OML for R interface for Oracle Machine Learning on Autonomous Database. And yeah, if you have any questions during the session, please put them in the Q&A section, as Sherry will be answering throughout our session. So our agenda for today, I'm going to start by talking about what ESA models are, explain them and some of their use cases, as well as compare them to other common text mining functions. Then we're going to move into talking about our specific Wikipedia model, then how to use that ESA model through OML for R, and give you a demo of what that looks like. So let's go ahead and get started here. Starting with ESA, which stands for Explicit Semantic Analysis. This is a type of model that supports natural language processing and was originally designed to help improve text categorization. Important part of it is that it assigns human readable labels to results. That's why it is an explicit model. And this is very helpful to help understand the results of this model. ESA looks to understand text as a combination of the concepts found in it, with the concepts just being individual words. And these concepts are organized into a vector space. So how does the model organize words in this way? When training the model, you start with your collection of texts. This is also commonly referred to as a text corpus. And with ESA, it's important that these texts are labeled. You can think about our Wikipedia example. The article is the text, and the label would be the title of that article. So first, the model looks to build an index, and this index is comprised of all of the words present in the documents that you are training on. This is important because the index is easily searchable. So once you have created your model, you can easily search up words and find the relevant information that you need on them for predictions. And what exactly is this information? For each word, you have a vector. And this vector includes scores, each of which scores how important the word is in every single document it appears in. So when you look up your word, you get a list, and that list comprises all the documents it's in and scores the word's importance in all those documents. And it's important that these scores are organized in a vector because that allows us to semantically analyze words and how they compare to each other. You can do math on vectors comparing them, calculating something called the cosine similarity between these vectors. And that helps you semantically analyze words and understand the relationships, looking at if words appear in the same articles, for example, or if they have high scores in the same articles, and understanding that to help relate words and analyze them. So what kind of use cases does this structure lend itself to? There's three main applications for ESA models. The first being word or document relatedness. In this case, you would input two different documents to your trained model, and it will return a score to you on a scale of 0 to 1 as to how similar those two documents are. Next, we have topic modeling, identifying the most important topics to a text. In this case, you would just input a single text to your model, and it returns the topics that this text is most about. Again, to our Wikipedia example, the topics would be the names of the Wikipedia articles. So you could feed your model a text and it'll tell you which Wikipedia article this most relates to. And finally, we have word or document classification, which is pretty straightforward, just classifying and labeling documents based on the labels present in the training documents. And I'd like to note here that there's three use cases here for ESA, but a single model couldn't do all three of these at the same time. That is because your document relatedness and your topic modeling use cases would generally be unsupervised models, whereas your word or document classification would be done by a supervised ESA model. So as you'll see later in our demo, these first two use cases can be done by the same model, but you would need a different ESA setup to do your word or document classification use case. All right, and this brings us to our second poll question of the day.
So for our second poll, we'd like to know about use cases. What use cases do you typically encounter for NLP? And please select all that apply here. And if you have a different answer, please enter it in the Zoom chat. Okay, it looks like an even split between Word document relatedness and classification, and then about 27% for topic modeling and 15% with other. If you'd like to share that with us, you can put that in the chat and that will go to just Miles and I.
All right, so moving on here, we next want to compare ESA to some other common text analysis models, being TF-IDF and LDA. And these are important to compare because both of these models are available through Oracle Text. So, we want to answer the question of why would you want to use ESA with Oracle Machine Learning on Autonomous Database versus these models available through Oracle Text. So starting with TF-IDF, it stands for Term Frequency Inverse Document Frequency. And similar to how we scored all of our words for every document in ESA, you also do that with TF-IDF, with scores increasing as a word appears more times in a document and decreasing if it appears many times in many different documents in the corpus. So the highest scores you'd find is for a word that appears many times in one document, but not in many documents in the corpus. Because if a word appears in many different documents, it's seen as just being generally common, and therefore its appearance in any one document isn't as important. This type of model is mainly used for information retrieval use cases. Pretty much any search engine you've ever used includes TF-IDF in its algorithm for getting search results. So that's mainly what this is used for. And it is similar to ESA in the fact that in both of these models, you essentially score words in each document in the same way, right? On how often they appear in that document versus other documents in the corpus. But ESA goes a step further to organize them in this vector space to get that set up to be able to semantically analyze words and the relationships. With TF-IDF, you're not really able to analyze the relationships between different words and different documents, more just the relationship between words and the documents they appear in. Moving to latent Dirichlet allocation. As Sherry mentioned, this is a really common algorithm for topic modeling, looking to group words into latent topics. The main difference between LDA and ESA, or a large difference at least, is in the names. That latent Dirichlet allocation finds latent groups where ESA finds explicit groups. Latent meaning just like hidden. So It basically means that the groups that are identified through this model do not have a label to describe them. They're seen as what's called as a bag of words. So it may understand that a lot of words are related, but there's no label to assign why they are related. For example, if you gave it a text about your dog, it may, decide the words pet and companion and fetch and fur are all related, but it wouldn't have that label assigned to it to say, these are all about a dog. So that's why it's just seen as a bag of words. Whereas with ESA, using those labels on the training data, it's able to identify and explicitly explain why groups are related to each other through those labels. So, yeah, in summary, ESA is explicit, which differs it from LDA, and then also the different use cases that it's available for differentiates itself, because TF-IDF is, again, mainly for information retrieval, LDA for topic modeling, but ESA, as we showed, has those 3 use cases, making it more versatile than these different algorithms. So we've talked a lot about ESA, but I find it kind of confusing to really understand how these models make their predictions on text. So I want to walk through an example with an ESA model making a prediction on a text for a topic modeling use case. So we're going to get into that here. So with ESA, we're looking to understand text as a combination of the concepts in it. So if we were trying to make a prediction on this sentence, my favorite NBA player is Michael Jordan. So first, our model would identify those concepts within the text. This function would avoid common words like my or is or the. These are called stop words, and they're not really important for semantic analysis, so they're ignored. And then for each of these important words, our model would go and look up the vectors associated with them, right? So for example, for the word NBA, the top of our vector might look like this, right? With NBA being most important to the article for the National Basketball Association, followed by these. Or for the word Michael, it might look like this, being most important in the article for just the name Michael, followed by some other ones. So looking up every vector for all of these concepts in the sentence, it can then, analyze these vectors, look at the cosine similarity between them, and try to find a topic that this sentence is most about. It would probably come to the result that this sentence is about Michael Jordan. That's pretty obvious to people, but harder for a machine learning model to figure out. But it can do that through this type of semantic analysis model. So that is, in basic terms, the process that an ESA model might go through to make a topic modeling prediction on a sentence like this. So we've explained a lot about ESA in general. What about this specific pre-built Wikipedia model? So this is a very large model created on millions of Wikipedia articles, reduced down to being about 200,000 topics. And there's 21.7 million features on this model. Later, when I go through the demo, I'll show you exactly what comprises a feature. But a big reason that we use this model is that Wikipedia is publicly available and easy to access. It's a huge data source of labeled documents that cover tons of different topics, easy to access. So it's really commonly used for ESA applications. If you do your own research and start looking up ESA, you'll find that Wikipedia is by far the most common text corpus used for ESA use cases. And Wikipedia serves as a general domain for ESA models. This means that the training data, the Wikipedia data used, is not about any one specific topic. So, Wikipedia has articles about everything, from science to history to pop culture. So we are not training our model in any specific domain. And that's good because it means you can make predictions in any type of text, right? You're training the model and helping it understand semantic relationships in all these different domains. So you can then make predictions on, any type of text you want to throw at it. And those predictions are quite meaningful. But there may be ESA use cases where you want to use something called a specific domain, basically meaning that the data that you train your model on is on a specific subject. And that basically reduces noise in your predictions from relationships that are not really in the subject area that you are interested in. For example, if you were looking to make predictions on a bunch of biology texts, and you had an article about bears and one about bulls that you wanted to look at the similarity of, back to our Michael Jordan example, Chicago has the sports teams, the Chicago Bulls and the Chicago Bears. So in looking at the similarity between your two articles, your ESA wiki model might understand that on the Wikipedia page for Chicago, these two things are mentioned and increase the semantic similarity between those two articles because of that. But, those sports teams have nothing to do with biology. So that's the type of relationship that you probably wouldn't want to encapsulate in your biology texts. So in that case, you might want to use a different corpus, some biology texts or encyclopedias, or maybe just a subset of Wikipedia articles to just be about biology to take that noise out of the predictions you get. All right, so how do we go about using this Wikipedia article in the context of Oracle Machine Learning for R? We're going to do that through the or.odm ESA function. This OML feature extraction algorithm was first released with database 12c, and then a classification version came along with 18c. So our feature extraction version is an unsupervised version of the model for our topic modeling and document similarity use cases, whereas the classification version is supervised and for our document classification use cases, obviously. So I mentioned earlier that you can't do all three use cases with one single model. So this is kind of showing that there's two different versions depending on the use cases that you are looking to do. So once we've trained our model with our or.odm ESA function, there's two functions you should be aware of for making our predictions. The first being feature compare, which is for that document similarity use case, how similar are these two texts, score that on a scale of 0 to 1. And then our predict function for our topic modeling use case, looking for the topics that best fit with a text. I'd like to note here too, a great benefit of doing this machine learning on this platform is, again, that this is all happening within the autonomous database. So we do not have to move our data to make predictions to our machine learning. So this makes this a very efficient setup to do our ESA model on. So without further ado, I'm going to jump over to our demo here. All right. So now we are in our machine learning notebook. And this one starts by giving a little explanation about ESA. We've talked plenty about that already, so we can move on. So before we use our ESA model, we first need to set some settings and policies. Here we are setting policies for our lexer, which basically is settings for how we will handle and analyze text in this text mining model. So we set it to our basic lexer and then give it the attributes index, stems, and English. English obviously defines that we are using the English language for this model, but index stems turns on a stemmer, which basically reduces words to their stem to be recorded as attributes for your model. For example, if you were training on a document that had the words, eating, ate, and eats in it, it would reduce all those words to their stem of eat, and then you could have a single feature for the word eat rather than having all 4 different features for those different versions of the word. So this kind of cleans up our model. It makes sense that you wouldn't need different features for all those words that are essentially talking about the same thing. So having index stemming on does that. So I mentioned how this is a very large model, and that means that it is preloaded onto autonomous database. We're not going through the process that you'd commonly see of loading in our training data and then training the model in the notebook and then making predictions. Because this is trained on millions of Wikipedia articles, that doesn't make a lot of sense to do that. So we just have our preloaded version of the model. And later on in this presentation, Sherry will be going over how you go about importing this model into your database to be used in Oracle Machine Learning. So we check to see that our preloaded model is available. We can see that we have Wiki model and that it is the feature extraction version of the function, not the classification one. So we're all set. Then the last thing we need to do to access this model is create a function to get the proxy object. So there's a lot going on here. I would just draw your eyes to the last line here where we make our or.odm ESA function call. And the rest of the lines up here are basically gathering and querying different information to be put into this function call to get our Wikipedia model. So we have our custom function, we call it, and we get our proxy object. We can look at our model here. On the left, we're checking out the first 100 features out of the 21.7 million ones present in our model. And And so to understand every feature, our feature ID here is the name of a Wikipedia article. And then attribute name is a word present in that article. You can forget the text dot at the front. Everything that comes after that is a word present in this article. So the word Alabama is present in this article. And then if we come over to the right, we have the score associated with that word for how important it is in the article. And you can see these words have varying importance. So that is what takes up a single feature. That lines up with the structure I mentioned earlier for ESA models. We have, an article, a word that appears in it, and then the score for that word in that article. On the right, we have some basic settings for our model, and we can move down here and start looking at some predictions using this model. Our first prediction here is just a simple one. This is our topic modeling use case to start. You can see we have our predict function that we are using, and we're just starting with the simple word bank as our first example. You'll notice we're not just predicting on an R data frame here. We're using our or.push statement to push this word bank to the database and get a proxy object to that. That is because with Oracle Machine Learning for R, everything happens in the database, right? So we need to push this data to the database to then make a prediction on it. So we get our tempdf proxy object to our word in the database, and we can make our prediction. So for our topic modeling use case on the left here, we get the topics or names of Wikipedia articles associated with this word. And we're given a whole list of them in this case, the top 10 topics, as well as the score for how much they line up with this word we are given. So banking in India, in Australia, Bank of America, these results all make sense for the word bank. Moving down to some longer examples for topic modeling, we try the word NFL games and get National Football League as our top result. That makes a ton of sense. And we move into a longer example here with a text about using R on Oracle database. Looking at our results, database is a top result. That makes sense. We also get machine learning, Oracle Corporation. All these topics seem to line up. And our last two examples, some longer ones here. We have a text about OML for Spark, and we get some more results that make sense. And a longer text about Oracle Machine Learning AutoML UI. And machine learning is our top result, data modeling, user interface. These topics all line up well with our text. So that's our topic modeling use case, and we can now move into our document similarity use case. So again, our input this time is going to be 2 texts or 2 words rather than 1, and our output is a single similarity score for those 2 texts. So starting with 2 simple words, we have fish and salmon, and they get a pretty good similarity score. But if you compare fish and hawk, as you'd expect, you get an incredibly low similarity score. Moving to some examples with longer texts, we have 2 texts about machine learning, one about regression and one about classification. And again, we get a pretty solid similarity score. But if you compare our machine learning text about regression with a text about geography, that similarity score drops off as you expect. And our last 2 examples for the document similarity use case, I think these are pretty interesting. Our first one on the left is text about Oracle Machine Learning for R and text about SailGP. Now, you wouldn't expect sailing and machine learning to be related in any way, but we get a pretty hefty similarity score here. And that has to do with the fact that Oracle is involved with SailGP, and obviously Oracle is involved with Oracle Machine Learning for R. So those semantic relationships are expressed in the similarity score. You can also see that even though this second text is about SailGP, it mentions analytics and data, which are also words referenced in our OML for R text. So that also increases our similarity score. And to finish up, we have 2 texts about Oracle Machine Learning for R and Oracle Machine Learning for Python. Of course, these are very similar subjects, as you'd expect, so we get a really huge similarity score for these 2 texts. And that is it for our demo of the notebook here. So let me hop back to our slides to continue our presentation. All right. So to recap what we've gone over so far, we explained what ESA models are and how they look to understand the semantic relatedness between words using explicit topics. We then compared ESA to TF-IDF and LDA and talked about how they're different and similar and why each of them is important. We then talked about our pre-made Wikipedia model, how it's a great general domain for ESA, but there may be situations where you want to use a more specific domain to train your ESA model on. We then moved into using this Wikipedia model through Oracle Machine Learning for R using the or.odm ESA function. And I would just like to note that we showed off this wiki model through OML for R, but you can also access it through the SQL and Python interfaces of Oracle Machine Learning on Autonomous Database. So we still have a few more things to go over here before we finish up, the first of them being our final poll question.
Okay, for our final poll, we would like to know, now that you have seen this presentation, how confident are you that you could get started using the pre-built Wiki ESA model? Okay, thanks for voting. We have about almost a 44% split between modestly confident but need more experience. And I'd want a deeper tutorial to apply this, and about 8% so that they are confident that they could jump in and start using ESA now. So the next thing, I'm going to show you briefly how to install the pre-built Wiki ESA model. And so we've created this notebook for you to make it very easy for you to get started with the wiki model. So it's a very large model. I think it's about 800 meg. And so doesn't come shipped with the database. You have to import it into your autonomous database. And some of the paragraphs in this notebook are repetitive from what Miles covered. So I'm just going to scroll down to exactly what we need here. The first thing that you can do is download the model zip file from this Oracle's open source software machine learning models. And this is the model for database 19C here. We have one for 12C as well. And then you can download it. It's this zip file, and inside the zip file is this model dump file. And that's the model dump file name. And then what you would do is upload it to your Oracle Cloud Object Storage bucket. And that can be a public or private bucket. But what I've done to make it super simple is I've uploaded this to a public bucket for users so they can just run this notebook and import the model. And the rest of the instructions use the public bucket that I've created. So there are a few grants. In SQL Developer, the Oracle Machine Learning admin user needs to grant the OML user read and write on the data pub directory, because that's where we're going to save the dump file before we import it to the database. And then these are the text policy grants that Miles was discussing in his presentation. We need those grants to work with the model. And then the next step is to copy the model dump file from object storage to the autonomous database data pub directory. And we're going to use the DBMS Cloud get object procedure to do that. And here it is. The credential name is null because it's a public bucket. And these instructions that I've linked here show you how to create a credential if it's not a non-public bucket. And this is the URI to the dump file in the public bucket, and then the directory name where you're going to be copying the file, data pub directory. And then you can use this SQL statement to verify that the model dump file exists in the data pub directory. This is the dump file, the size of the model dump file, and when it was created. And then we'll just import the model to the database. So the dump file is saved in the data pub directory in your autonomous database. And so all you need to do is use this DBMS data mining import model procedure to import the model. As you can see here, I'm dropping the model first as a cleanup step if it exists. And then I'm doing the import. So I'm providing the file name and where the file resides. So this is the wiki model dump file. This is the file name, and the directory is the data pub directory. And I'm remapping the table space to the current user's table space, which is OML user, and the source table space was DM user. So we do a schema remap that's required. And I confirm the model is imported correctly. I can see the model name, the mining function, the algorithm, and when it was created. And then the next thing that you need to do is set up the text policies, which Miles already covered in his notebooks. And as he mentioned, you'd now be ready to use the Wiki ESA model, and you can use it from OML for R, OML for Pi, or OML for SQL. And we have notebooks in our template notebooks for each of these. So if you go over here to the 3-line menu and templates and examples, today you'll find the ESA notebooks for OML for Pi and OML for SQL, and very soon you'll see when they're for OML for R, when OML for R is released on Autonomous Database later this month.
All right, thank you, Sherry. Just in closing here, as you may know, these slides are available for download after our session. So we've included some links to some more information about OML for R documentation, and then ESA documentation for OML for SQL and OML for Pi, because as we've mentioned, it is also available through those interfaces. So with that, I'd like to say thank you all for coming and listening to us today. And if you have any final questions, please put them in the Q&A, and thank you for your time. And Sherry, were there any interesting questions throughout the session that you'd like to iterate more on?
Yeah, one question that came up was, can I use the Wiki ESA model on Oracle database on premises? And it is available for Oracle database on premises today. So if you have an Oracle database, you can, for free, just download the model and get started using it. Another question here is, do we need to install OML for Pi? And for Autonomous Database, you do not need to install anything unless you're using the universal client. But on premises, you would need to install the server and client portions to use OML for Pi and the Wiki model with OML for Pi. But if you wanted to use the Wiki model with OML for R, you would not need to install OML for Pi. And do we have pre-built models for sentiment analysis? I'm going to ask Mark to chime in here, but we don't have a pre-built model for sentiment analysis for Oracle machine learning, but we might have something in Oracle text that we could look up. I am not sure.
I'd say for sentiment analysis, the closest we have, you could look at the cognitive text for OML services.
Yeah.
But okay. Otherwise, no, I mean, it's not specific to sentiment analysis for ESA.
Okay, I think that's it. Thank you, Miles, and thank you everyone for joining, and we'll see you next time.